We'll now talk about oxidizing and reducing agents. So we'll take a look at this reaction. We have zinc plus Cu2 plus going to zinc 2 plus copper. I want you to determine what the oxidizing agent is in this reaction. This is a concept that we discussed previously in Chem 1A, but we're going to do this as a little bit of a review here. So tell me, what is the oxidizing agent in this reaction? All right, having given you some time to think that over, hopefully you remember how we're able to determine this. What we need to do first is take a look and see what has been oxidized in this reaction. So in this reaction, zinc has been oxidized. It's lost electrons to go to zinc 2 plus. But the question is not asking what's being oxidized. The question is asking, what is the agent that is responsible for oxidizing the zinc? What is causing the zinc to be oxidized? So we look at the reaction and we see what is reacting with the zinc to make it oxidized. And that would be the Cu2 plus. This is the agent that is responsible for oxidizing the zinc. All right, so Cu2 plus is the oxidizing agent. Now we could take this a little bit further if we wanted to, and also bring in the concept of reducing agents. So in this reaction, Cu2 plus is reduced. It gains 2 electrons to go from Cu2 plus to Cu solid. And then you can ask, okay, well, what's the reducing agent? Well, what caused the Cu2 plus to be reduced? That would be the zinc. So Zn causes Cu2 plus to be reduced, and that makes Zn the reducing agent. We have this sort of complementary relationship that exists between oxidizing and oxidizing agents and reducing agents. In a redox reaction, the thing that gets oxidized is the reducing agent, and the thing that gets reduced is the oxidizing agent. Right? There's that complementary relationship that exists here. Now let's talk about how information like that gets encoded within the table of standard reduction potentials. In this table of standard reduction potentials, all of these reactions are written as reduction half reactions. So everything that's on the left-hand side of the table is being reduced, right? Now, previously, we had said Cu2 plus, it gets reduced, that's considered an oxidizing agent, right? Anything that's getting reduced is an oxidizing agent, like our Cu2 plus. And so, on this table, everything that's on the left-hand side of the table is an oxidizing agent. Everything that's on the right-hand side of the table is a reducing agent. For instance, zinc we determined was a reducing agent here, and zinc shows up on the right-hand side of the table. So everything on the right-hand side of the table represents a reducing agent. That is a really helpful thing to be aware of in terms of how this table is organized. Oxidizing agents are going to be on the left-hand side of the equation, and reducing agents are on the right-hand side of the reaction arrows. Now, additionally, because of how the table is organized, you can learn a lot about the relative strengths of the oxidizing and reducing agents. Because when we take a look at the oxidizing agents, with the way that this table is organized, the value of E naught increases as you go up the table, meaning that this reduction half reaction becomes more and more favorable, more and more spontaneous, right, as you go up the table. And so what that means is that the oxidizing strength increases as you go up the table. F2 is a much stronger oxidizing agent than Li+, because the reduction of F2 has a half cell potential of 2.87. So it's a really big positive number, and that's going to be really favorable towards the potential spontaneity of a chemical reaction. It's going to make it more likely to occur, and so F2 is going to be more likely to cause oxidation to happen than Li+, which has a negative 3.05. On the flip side, the reducing agents increase in strength as you go down the table. And so Li solid is a much stronger reducing agent than F-, for instance. All right, so having introduced this, we're now going to talk about how you can use the table of standard reduction potentials to make predictions of spontaneity for reactions.